Before we begin our study of infinite series and improper integrals and sequences, let's review limits. You studied them in Calc 1 in Section 4.2. As I've mentioned to you before in class, the concept of limit is really the only new idea that you're introduced to in the entire calculus sequence. It's the only new idea since high school. So it's needless to say, it's very, very important. So we'll begin by just looking at the curve y equals 1 over x for x greater than 0. And let's just look at three different limits. As x approaches 3, the limit of f of x, or the limit of 1 over x, as x approaches 3 is equal to, well, that's pretty easy. It's equal to 1/3. You just plug it in, don't you? Look at the point. Let's say this is x equals 3 right here. And here's the point, 3, 1/3. The function is continuous at x equals 3, so we just plug in x equals 3 to determine the limit. Now for the next one, the limit as x approaches 0 from the right. So we're coming in, remember the little plus sign means from the right. And in this case, I guess it also means positive. So we're coming into 0 from the right, and we see that the graph is just rising. And in fact, we know that there is a vertical asymptote with equation x equals 0. The y-axis is a vertical asymptote, and that's what we mean when we say the limit as x approaches 0 from the right of 1 over x is, well, it's not really a limit. I put equals infinity there, or you could put equals plus infinity to indicate that 1 over x is getting large without bound as you approach 0. So really there is not a finite limit, but we often use this notation, the equal sign. Now, let's look at this function 1 over x as x becomes large without bound, as x approaches infinity. Well, we know what this means. We know that we have a horizontal asymptote with equation y equals 0. That means that the limit of the function as x approaches infinity is equal to 0. So we have a finite limit in two of these cases, and in the other we indicate plus infinity just to show that we know what's happening to the function as x approaches 0 from the right. Reviewing the definition of continuity. You should know this definition. A function f is continuous at x equals a if the limit of f of x as x approaches a is equal to f of a. So this definition here, don't just think in your mind, oh, it's a smooth curve, it passes through the point. That's true, but the definition is in terms of limits. And in order to prove things later on in your career in mathematics, in order to prove theorems, you have to know the formal definition. Many limits then are evaluated by just plugging in x equals a. For example, the limit of sine x as x approaches pi over 2. Well, the function is continuous at pi over 2, so it's simply the sine of pi over 2, which of course is 1. So we have a limit of 1. Likewise here, as x approaches 2, we get 2 minus 2, 0 on the top. On the bottom we get another constant, 3, and that is equal to 0. So if a function is continuous at x equals a, to evaluate the limit of that function as x approaches a, you plug in x equals a. The reason that you see arctangent so much in Calc 1, 2, and 3 is because it is a function that has a horizontal asymptote that is not a rational function. So you'll see it in lots of your work in calculus. It's a good example. The limit as x approaches infinity of arctan x, we know, is pi over 2. That means that we can make this we can make f of x, we can make arctangent x as close as we want to pi over 2 by just going far enough out on the x-axis. It gets closer and closer and closer. Quite often when you take limits in any context, you will write the function as a quotient and try to take the limit by looking at the behavior of the numerator and denominator functions. So let's look at the different possibilities for the numerator and denominator functions. The limit as x approaches a of n of x over d of x. Now remember that a could be infinity. This goes for any value of a, also plus or minus infinity. Okay, so let's just look at the different possibilities, and I'm going to use a real informal notation here. I'm just going to put n over d, okay, instead of as functions, and I'll use green to show what's happening to these. Okay, well, first of all, the numerator could be approaching a constant, k1, and the denominator might be also approaching a constant, k2, which is not 0. In that case, we say that the function itself, n of x over d of x, is approaching k1 over k2. You probably have a continuous function in this case where you just plug in x equals a. Another possibility would be that the numerator approaches a constant. Maybe the numerator, as x approaches a, is approaching a constant, which is not 0. And the denominator is approaching 0. Well, if the numerator is approaching a constant, like 3, and the denominator is shrinking, then, or in fact, think of it this way. If the numerator is approaching a constant like 1 and the denominator is going to 0, we know from looking at the graph of 1 over x as x approaches 0 that the quotient blows up. If the numerator is approaching a constant and the denominator is approaching 0, then we have the function itself is becoming, well, plus or minus infinity, I'll say. It's blowing up. There is no finite limit. For example, if we had the limit of arctan x over the sine of 1 over x as x approaches infinity. Let's see. Well, the arctangent of x as x approaches infinity, the numerator function, is approaching a constant pi over 2, and as x approaches infinity, 1 over x is getting very close to 0, so this is approaching the sine of 0, or 0. Now, if you just take out your trusty calculator and put in x equals 1,000,000, you'll see that this quantity here is, oh gosh, it's way more than 1,000,000 itself. So as x approaches infinity, this quotient becomes large without bound. So what about if we have n over d, where the numerator is approaching a constant still. Numerator is approaching a constant, but this time the denominator is blowing up. It's going to plus or minus infinity. Well, think of 1 over x again. The numerator is 1, and the denominator, as it becomes large, the 1 over x goes to 0. And of course, that's exactly what happens here. Any quotient where the numerator is going toward a constant or is a constant, and the denominator is blowing up, then the whole thing approaches 0, or we could say the limit is 0. I could show you an example. 1 over x is an example, but we could also look at maybe the sine of 1 minus 1 over x squared. Now I'm not writing the limit there because I'm going to use this informal notation. I'll use an arrow, meaning that I'm taking the limit. Okay, we're looking as x approaches infinity. So, as x approaches infinity, well, let's see, 1 over x close to 0, so this is just approaching the sine of 1, whatever that is. And the bottom, x squared, is approaching plus infinity. So we say then that this quantity, if I had written limit out here, I'd say equals 0, but I didn't write limit, so arrow will mean that we're taking the limit, and we would get 0. So far you've had 3 cases, numerator over denominator, and in each case we had the numerator approaching a constant. The denominator might approach 0, it might become large without bound, or it might approach a constant also. So we have a couple more cases to look at. The numerator might approach infinity, might be getting large, or I should put plus or minus infinity. The numerator might be becoming unbounded, and the denominator becoming a constant. Well, in this case, if the numerator is getting huge and the denominator is just stabilizing at some constant, then you know that the whole fraction, the quotient, is becoming unbounded. So it's plus or minus infinity. There would be no finite limit in that case. Now we have another case. What if the numerator over the denominator, what if the numerator was becoming unbounded and the denominator was becoming unbounded? Or what if we had n over d, where the numerator was approaching 0 and the denominator was approaching 0? Well, there we don't know, and so that will be the topic of our next slide. Let me go back up here to this one and see if I can think of an example. Numerator becoming unbounded over denominator a constant. Well, let's put x squared on the top, and the bottom we want to go to a constant. So, well, how about the sine of 1 minus 1 over x again? Now, if we look at this, we see that the top is definitely approaching plus infinity. As x, we're looking at the limit as x goes to infinity, by the way. All of these I'm looking as x approaches infinity, because that's what we're going to use in our study of sequences and series. Okay, so the top is becoming unbounded in the positive direction, and the bottom function, well, as x goes to infinity, we know 1 over x goes to 0, so this is getting close to the constant sine 1. And you can see that this, of course, is just getting huge. So the limit, again, I didn't write LIM, so I'm using an arrow to show that I'm taking the limit. And you just assume these limits are as x goes to infinity unless I write otherwise. So this also becomes large without bound. Okay, well, let's look at the 2 cases where the numerator and denominator both are unbounded, or the numerator and denominator both approach 0. We can't tell if the limit exists. It may or may not. These are called indeterminate forms. You studied them in Calc 1, and you can look in your book in the index and find indeterminate forms and read about them. There's far more than just these 2, infinity over infinity or 0 over 0. But in these cases, in these particular cases for indeterminate forms, you can use L'Hopital's rule to find the limit. And this rule is not proven in our text, and in fact, probably you won't see a proof of it as an undergrad in math. But it's just so useful that we give it to you, and I think you'll be able to see intuitively why it works. The limit of n of x over d of x as x approaches a, if you have one of these indeterminate forms, is the same as the limit of the quotient of their derivatives. Okay, so always first make sure that your function is written without negative exponents so you can clearly see what's on the top, what's on the bottom. Well, the first one is written that way for us. And so we look at the numerator and denominator, the limit as x approaches 0 this time. Okay, so sine x approaches 0 as x approaches 0, and x approaches 0. So this is of the indeterminate form 0 over 0. So I'm going to write, well, I'll do this one a little more formally. I'll say equals, and I'm going to put LR here. So you will know when you look at your notes that we used L'Hopital's rule. So this is equal to the limit as x approaches 0 of the quotient of their derivative. So it will be cosine x over 1. Oh, well, now we can calculate the limit. We know that as x approaches 0, cosine approaches the cosine of 0, which is 1. And so I can now write equals 1 over 1 is 1. Notice the difference in my notation. When I'm using the limit notation, I still put this little green on here just to show myself what's happening. But I use equal sign. I'm not using those arrows. Okay, so in the next example, I first want to rewrite this as the limit as x approaches infinity of e to the x over x squared. You don't use negative exponents because you won't clearly see what is the numerator function and what is the denominator function. So now we look at each one of them separately and we see, well, of course, as x gets big, e to the x gets bigger faster. So that approaches infinity, and x squared also is unbounded. So we have the indeterminate form infinity over infinity, which tells us that we may use L'Hopital's rule. Sometimes it helps, sometimes it doesn't. But it will here. The limit as x approaches infinity of, well, the derivative of e to the x is e to the x, and the derivative of x squared is 2x. Well, we still have the same problem, don't we? E to the x becomes unbounded, and so does 2x. So we have the same indeterminate form, and by the way, put LR there, meaning that we're using L'Hopital's rule. So I'm going to use it again, because I still have infinity over infinity, and I use it again, using L'Hopital's rule again. We'll say this is equal to the limit as x approaches infinity of the derivative of e to the x is e to the x, the derivative of 2x is 2. So now I'll use, well, what we talked about before. This is 1/2 e to the x, and of course that becomes infinite. So I'll put equals infinity. Of course, it doesn't mean that it is a finite limit. Now our last example, I know when you have taken limits of rational functions since high school, and so you may know a trick for this, but I just want to show you the use of L'Hopital's rule. Here we have two polynomials. You know the behavior of the polynomial as x approaches infinity just by looking at its leading term. So we see x cubed and 4x cubed. So we know that we have the numerator polynomial and the denominator polynomial, both becoming infinite, positive infinity. So I could use L'Hopital's rule. Now, I know a lot of you already know that the limit is 1/4, but just see how you can use L'Hopital's rule in getting this. So using L'Hopital's rule, I would take the limit as x approaches infinity of 3x squared minus 2 over what, 12x squared plus 18x plus 1. Well, again, we have infinity over infinity. Infinity and 12x squared is becoming infinite. So we have the same type of indeterminate form, and that allows us to use L'Hopital's rule again. So we have the limit as x approaches infinity of, what is that, 6x over 24x plus 18, and we could again say we have infinity over infinity, use L'Hopital's rule again, and we get equals the limit, well, I don't even have to write it, do I? The limit as x approaches infinity of 6 over 24. Those are both constants, so the limit is 1/4. Now, I don't expect you to use L'Hopital's rule with quotients of polynomials. If you know a faster way of doing it, by all means do it. I just wanted you to see various cases where the L'Hopital's rule is appropriate. You also learned in Calculus 1 that how to take limits when you have composite functions. If f and g are functions such that the limit of g of x as x approaches a is b, and f is continuous at b, then you take the limit, well, the limit of f of g of x is f of b. Now, I would not say memorize this, just you use it naturally, but be conscious of the fact that we are taking limits of composite functions. So in the first example, the limit of the cube root of 1 over x. Okay, what we've been talking about so far is just quotients. So you look under here and you see that quotient. 1 over x as x approaches infinity is going to 0. So this is the cube root of 0, which is 0. Just kind of do it naturally, but you should be aware that you are using a quite powerful idea here. The other example I had for you is the limit as x approaches 1 of 1 over the natural log of x minus 1, that squared. So let's see. We have a quotient. The numerator, of course, is going to 1. It is 1, constant. And the argument of the log is x minus 1, the quantity squared. So it is positive, and as x approaches 1, it is approaching 0, and I'm going to mention from the right, because the natural log would not be defined if its argument could be negative. Okay, so now think of the natural log function. Here's natural log. And as x comes in towards 0, as its argument comes in towards 0 from the right, we see that the function is becoming unbounded in the negative direction. So let's see, I could use another color here. The denominator function then is going to minus infinity. So we have 1 over minus infinity, and that is, as we mentioned before, numerator going to a constant, bottom blowing up, we get 0. So here's some more examples. Okay, I don't want any exponents written that way, so I'm going to rewrite this as the limit as x approaches 0 of the sine of 1 over e to the x. So now I start looking on the inside. This is function composition. The outside function is sine. The inside function is 1 over e to the x. So I look at that 1 over e to the x, and I see that e to the x is becoming infinite, and so 1 over e to the x is approaching 0. So this limit will be equal to the sine of 0, which is 0. The next limit is the limit as x approaches infinity this time of the cosine, and again I want to write this as 1 over e to the x. You clearly see what functions are in the denominator and numerator. Well, again, 1 over e to the x, 1 over e to the x is approaching 0. So the cosine of 0 is our answer, which is equal to 1. Now, the next example, we're taking the limit of the natural log of 1 over x, and we see that as x approaches infinity, 1 over x approaches 0, and since we're talking about the argument of a natural log, I'm going to double check to make sure that this function is defined, that the problem makes sense. And yes, 1 over x approaches 0 from positive values. So this, let's think again. Think back to your natural log. That graph should be in your mind. You should not have to use a calculator to graph that. You see, as its argument comes into 0 from the right, the function is becoming unbounded in the negative direction. So we say this is minus infinity. Another very useful theorem about limits is the Squeeze Theorem. I'll refer to it as SQT. Suppose that g of x is always between f of x and h of x on an interval containing a. If the limit as x approaches a of f of x is equal to the limit, if the limit of this function as x approaches a is equal to the limit of that function as x approaches a, and g of x is always in between, well then g of x has exactly the same limit. Note a can be infinite, and an interval containing infinity is just an interval of the form, an open interval of the form b comma infinity. So let's look at this one. Sine x as x approaches infinity. Well, here, the numerator, I can't say it has no limit, right? It's not becoming unbounded. It's wavering around between 1 and minus 1 forever. So I can't use what we've talked about. I can't use the different ideas that we've talked about when we have the quotient of two functions. It doesn't work. But I know that sine x is trapped between the function y equals 1 and the function y equals minus 1 for all x, so certainly at any interval containing infinity. So this implies that, all right, now listen carefully, x is becoming large without bound. So certainly I can assume that x is a positive number, and if I write 1 over x, if I divide all parts of this inequality by x, it's positive, and so the inequality sign remains in the same direction. You have to be really careful with inequalities. Okay, well, this does it because we know that 1 over x approaches 0 as x approaches infinity. Minus 1 over x approaches 0 as x approaches infinity, and so by the Squeeze theorem we have found the limit, that this limit here is equal to 0 by the Squeeze theorem. And when you're writing, if you have an inequality like this and it's in the context of taking limits, you can just use these arrows and show me the left-hand side goes to 0, the right-hand side goes to 0, and then you can conclude this. But mention what you used, L'Hopital's rule, Squeeze theorem. How are you making the conclusion that you make? In our use of limits in the topics that we'll cover for the rest of the semester, it's important to know these graphs here in your mind. You need to know how they grow, their rate of change. In other words, their derivatives, because we're going to be using L'Hopital's rule quite a bit. Look at these functions. Here's natural log x. Natural log x is kind of like the slowpoke of functions that grow. All of these functions that you see here, natural log x, radical x, x squared, x cubed, x to any power. I could write here x to the n instead of just x squared, and e to the x. In fact, I think I will. Let me, this could just be x to the n. It doesn't have to be x squared, x cubed, x to the fifth. Natural log, they all get large without bound as x gets big. However, natural log x is the slowpoke. He doesn't get big fast. And any power of x, x to the 1, x to the 1/2, x to the 1 over 1/10, to the 1/10. Any power of x, the graph will eventually be higher than natural log x. And e to the x, exponentials, grow the fastest. So we have natural log is a slow grower. Powers of x grow faster than natural log, but not as fast as e to the x. This should be just something in your mind. Imagine these graphs in your mind and keep that in mind, and I'll show you now how we'll use it. Where you will find that comparison in your head to be handy is when you're looking at quotients of functions which are natural logs, exponentials, and polynomials. For example, if we're taking the limit of natural log x over x, we know that they both become infinite. But I'll use L'Hopital's rule to show you that still, even though x is getting large and natural log x is getting large, there is a limit, because we'll use L'Hopital's rule and we get this is equal to the limit as x approaches infinity of the derivative of natural log x, which is 1 over x. The derivative of x is 1, so this is just the limit as x approaches infinity of 1 over x, which is 0. Sometimes the limit exists when both the numerator and denominator become infinite. Now, sometimes it doesn't. But let's look at the next example. Natural log x squared over x. Well, natural log x squared is growing quite a bit faster than natural log x, so maybe there'd be a limit here. But you will find, using L'Hopital's rule, that if you have powers of natural log and in the bottom you have powers of x, that the limit will be 0. So let's take the limit of the quotient of their derivatives, 2 natural log x times 1 over x over 1. So that's equal to, simplifying, 2 natural log x over x as x approaches infinity. There, I just simplified. Now I'll use L'Hopital's rule again, and I'll get the limit of, as x approaches infinity, of 2 times 1 over x over 1. And we know that the limit of 2 times 1 over x is 2 times the limit of 1 over x. This is equal to 0. No matter how big your powers of natural log are, they are not going to beat x ever. Well, after x is big enough. X will grow faster than even natural log x to the 10th power. Not at first, but eventually, and we're talking about x going to infinity. The next one, we have infinity over infinity. X to the 10th will be much bigger than e to the x at first, but if you have a power of x over an exponential, eventually this quotient will begin to get smaller and closer to 0. Now, I'm not going to do it 10 times, but notice, if I used L'Hopital's rule here, I could take the derivative of the top, 10 x to the 9th, In fact, let's use arrows so I don't have to keep writing this limit. I'll just say arrow and e to the x. Arrow, well, I take infinity over infinity again, so I'd have 90 x to the 8th over e to the x. Again, infinity over infinity. And what you're going to get if you were to do it 10 times would be 10 factorial over e to the x, which of course goes to 0. A constant, this would finally become something, a constant on top and going to infinity on the bottom. You have the quotient then going to 0. I obtained these two graphs using Mathematica just to let you see what's happening, and we'll do a lot more of this in lab. But let's say we're looking at natural log x to the 4th over x. Well, at first, notice this graph here. I'm graphing it between 0 and 1,000. And the graph on the top here, the graph on the top is ln x to the 4th. You see, it's on top of y equals x for quite a while. That's all the way out to 1,000. But look over here at about x equals, oh, I don't know, 5,700 about, right here, right there, we see that natural log x, or y equals x, overtakes ln x to the 4th. Way out there, close to 6,000, but it happens. And now x is on top, and natural log x raised to the 4th power is on the bottom. And the numerator will go to infinity at a rate so fast that this limit will be equal to 0. Now you could use L'Hopital's rule 4 times and see that, but I wanted you to see how y equals x overtakes that function way out on the x-axis.